heat and cold test them, thermal cycle, power cycle, do all that stuff. And then you had a lot that was qualified. And then you chose from that the ones that would go into the flight instruments. So we had just delivered an instrument for Mars 01 when we left to go for training for Mars 98 operations. And then after the Mars 98 failure, the Mars 01 mission was canceled. So this is part of the roller coaster where you're going down. This lander was a copy of the Mars 98 lander. So they said, well, we don't really know what happened to Mars 98. I mean, you got 8 or 9 different possible causes. We're not going to fly the same design again, so they just put it in the storage. So it was stored in a clean room in Lockheed Martin. That will turn out to be important later. So we're struggling to find another project. So a lot of the people in the group left, and there was, 2 or 3 of us left, including Peter. And he got a project and some money to keep us alive and afloat to make a front end of a microscope for the European Beagle 2 lander. Now this was attached to the side of the Mars Express European Mars orbiter. And just before it went into orbit, jettisoned this thing, and it had its own heat shield and parachute and a crushable surface on it, and it landed on Mars. But they never heard from it. So,
just a stupid question. Flight time to Mars?
it's 8 to 9 months,
Thanks.
at least for the rocket Thru run. We built I got to design the whole front half and build it, and then the back half with the CCD and all the rest of that stuff, control electronics, that was done by the Germans. They integrated together and they took it to England where this spacecraft was being built, and they integrated it in the spacecraft. They didn't even have money to have somebody run the spacecraft and test to see if they could talk to the microscope. I mean, it should work, but anyway, so the guys that delivered it were really, they said this is not going to work. We're not testing anything, we're not checking things out. We just put it together and put it on the lander, and they told us thanks and go home. So they were really, they had a feeling it was doomed to fail. It appears, this picture is taken by the high-rise Mars orbiter. 2 of the 4 petals, here's the base part, and the petals are supposed to deploy out, and 2 of them did, but the other 2 didn't. And that means 2 of these petals were still wrapped up on there, and they covered up the antenna. So that's probably why we haven't heard from it, because we can't communicate. And without power from 2 of those petals, the battery didn't last very long, and it probably died. Another mission that was going on, now this is an instrument that an LPL researcher, scientist, had worked with Ball Aerospace in designing, and Ball built it. And while they were building it, their machine shop got too busy, and they needed some parts made for the focus system, so I took care of that and had our instrument shop make the parts and get them inspected and fill out all the mountains of paperwork we had to fill out to ship them back to Ball. Anyway, they became part of the flight instrument. A high-rise instrument is a spy telescope almost for Mars. It's a 20-inch F-24 Stigmat. It has 14 line-array CCDs at the focus. It takes images 20,000 pixels wide by 60,000 pixels long typically, but it can be any length until they run out of memory on the spacecraft. At 300 kilometers altitude, it has 12-inch per pixel resolution on the ground. That's why you can see those petals on the landers. It's a strip scan imager. That's the same way many Earth resources satellites are built. And as they fly over the surface, the image moves across the CCDs. They scan the CCDs at the same speed so they essentially freeze the motion on the CCD. So this is it's like a three mirror Ritchie kind of, and it's the focus mechanism moves this last mirror here to get the focus on the CCDs, which are down here. It's surprising with an F-24 instrument, you think, wow, that's really slow. They should have a huge depth of field, but because of the magnification they're working on, it's not. When the spacecraft goes from 300 kilometers to 400 kilometers, they have to refocus. If it goes up to 600 kilometers, which it did for some part of its orbit, they had to focus again. Later on, I'll show you a picture. They had to change the focus by a lot. This is what the instrument looks like in final assembly at Ball Aerospace. It's a pretty good sized camera. It's on the Mars Recon Orbiter. And this is the kind of pictures it can take. This is an avalanche in the polar region of Mars caught in the action by HiRISE. They just happened to be scanning that area, and a bunch of this edge right here, which is sublimating away and falling apart, slid down the slope. HiRISE can also image parts of landers and parts they leave behind. These are back shells and parachutes from a bunch of different missions.
Did they photograph Mars 98?
They have, but it's where it landed was fairly dusty, and they didn't get the spacecraft didn't get into a good position to photograph it for several months, and they suspect they think they know where it is, and they've seen it. The solar panels are not deployed; they just see a lump. So
that was the one that was fairly south, right?
Yes, it was.
So the high-rise may not even make them.
Yeah, no, it's in an orbit that does cover the poles. So, but the problem is when the sun is there and the spacecraft is there, sometimes that combination doesn't line up for months. So they can't like image it right away unless they plan for that. They didn't plan to do that, but they did for some other missions. Anyway, so everybody else left. It's just Peter and me in the group. And Peter's desperate to get a project. So NASA had another opportunity for a Mars lander mission at the next launch window. There was a bunch of people. Typically when NASA has an opportunity like this, they get 20 or 30 proposals. And out of those, maybe 10 are really good, solid, well thought out, well-detailed proposals that they really seriously consider. We were working on 6 of them. I don't remember some of them, but these are the ones I remember. There was a Mars balloon mission. They were going to land, have a balloon that would float around Mars, go wherever the winds took them, and it would heat up during the day and fly during the day, and at night it would cool off, land, and descend, and stop on the ground. And so it would kind of do that all around Mars. And I designed 3 cameras for them, and gave them some drawings and some optical performance, and this is what you can expect, this is how much it'll weigh, and all that stuff. And there was the Mars Polar Drill. This mission was going to melt its way down through the Mars polar cap, the water ice polar cap. They were going to land an RTG, which would generate 5 kilowatts of electrical power, and they would power this probe, and it would just melt its way down through the ice. In that ice, all the layers they would see would be records of all the ash falls and dust storms and everything else that are trapped in like our Arctic caps. So that one was interesting. They said, you can have as much power as you want. You want 100 watts? I'll give you 100 watts. We're going to put 5,000 watts in the heaters in this probe, so 100 watts for a camera is nothing. We've always had very stringent power budgets. We had to count all our watts, and we counted grams for mass. I mean, you had to be very careful with your design. But not for power for that one. And then the last one was Mars weather monitors. This mission had 18 Mars landers that would all be scattered around the surface of Mars. They were small. They were about 4 inches in diameter and about 14 inches long. They looked like a bullet. They had tail fins. They were hard landers. No parachutes, no heat shields. They came screaming into the atmosphere. They had a ablative on the front. They had a crushable section because they literally hit the ground. If they landed on dirt, they would see about 300 Gs. If they landed on a rock, they'd see about 1,600 Gs. So we had to design a camera for that. So I designed a camera that stands It's like being fired from a gun. Only in the reverse. Anyway, I did something. I made it work. I tested it. It withstood 1,600 Gs of shock. It had commercial parts in it. We didn't have much money, we didn't have much time, so we did what we could. But we proved the concept would work. The PCB was an inch in diameter, the size of a quarter. And it had a CMOS imaging chip on one side and a PIC microprocessor on the other and a few passives around. I tested it down to minus 150 C. It even worked down there. The images were junk, but the image chip actually worked at minus 150 C. These were all commercial parts, no colder than 0 C. Anyway, the last proposal we worked on was one to rebuild and fly the Mars 01 lander. And the stereo camera on there was going to be a hot-rodded SSI. By that I mean we were going to use much bigger CCDs with a lot more resolution, but it'd still be a stereo camera. Try and keep as much heritage as we could in the hardware. We'd also reuse the rack and the optical microscope from the Mars 01 instruments. The CCDs came from Spirit Opportunity rover mission, which had just launched. So they had a whole bunch of flight spare CCDs. Did we need it anymore? Excuse me a minute. So we won. All the people we worked with, I think, were kind of annoyed with us, but anyway. And Peter was the PI on the mission, not just the PI for this instrument, he was the PI for the mission. Which means he was responsible for the whole thing, the rocket, the whole budget, the whole thing. This is the first time they did a mission like this where a non-NASA person was the PI for the whole project. This time the lander was going to the Martian North Pole and included the robotic arm that could dig into the ground. There was another LPL-built instrument, the gamma ray spectrometer, that was on the Mars Odyssey orbiter, that showed there's large amounts of water. They detected hydrogen, but that means water in the top meter of soil. And so we landed south of where the polar cap was, away from the polar cap, but where there was what they call patterned ground, which is a type of ground that appears in Arctic regions where they have freeze-thaw cycles, and the ice underground breaks up into roughly hexagonal or pentagonal blocks. And so you have this pattern you can see even from the satellites. So they were really sure there was going to be water ice close to the surface here. So we built this new camera for the mission, the hot-rodded SSI. And I got ribbed by that because they said, oh, you car engineers come up here and think you can design us a hot-rodded camera. So here's our hot-rod SSI, and it's even got a hood bulge. So we kept the camera pretty much the same. You know, large parts of it were copies of the Mars 98 Pathfinder SSI. But instead of an image that had 256 by 256 pixels for each eye, we had a 1K by 1K CCD. So the field of view was the same, but we had 4 times the resolution. So I got to design the optics and all the internals and pack all this stuff into a case that really wasn't that big, and that's why we ended up with that. So that's the whole camera. The mask is the same. The camera got quite a bit heavier because we had so much more stuff inside. Keep pushing the on button. This is the filter wheel. There's the bearing for it. The motor's hiding behind this connector. These are the bottoms of the circuit boards for the detectors. Here's the 2 covers for the 2 CCDs. We've got 2 individual CCDs now, 1 for each eye. And we jammed all this stuff in here, and it sort of fit. This is what the optics bench, there's the lens. Lenses were still relatively slow, like f16. But the light came through here, bounced off a prism, and then came up at an angle, so the two light paths deviated, and we could fit each one into a CCD. This is what the filter wheel looks like. It's really fun torquing all these little screws and not slipping off and damaging the filter. That's always, when you get that done, you say, oh, geez, go home and just relax now. So this is black paint. This is one of the full mirrors, the mirrors in there. And this is the aluminum part that holds it. This is not black paint. This is something called martenite. It's an etching process they apply to aluminum parts that makes them have lots of microscopic pyramids on the surface, and they're black pyramids. So light hits it and bounces down into the spires of the pyramids and doesn't come back. This stuff is really black. It's also very fragile. If you touch it, it turns gray. So we have to handle this very carefully.
How does it apply?
It's not applied. It's like an etching process they do to the aluminum. So you send them a bare aluminum part and they send it back like that. So this is the robotic arm camera. This is the Mars 01 camera with the new LED lamps. There's all the little LEDs in there. What you can't see is there's a portion of the lamp housing that shines light down, because when you're looking at the tip of the scoop, it's a half an inch away from the front of this window. So these lamps here aren't going to light it up, and these here aren't either, because the scoop is up here. So they go below the scoop, and these are shining in the back of the scoop. So we had to have another set of lamps that shone down to get that front of the tip illuminated. This is the microscope that we built for the Mars 01 instrument. The MECA, Mars Environmental Compatibility Assessment, got renamed. They still call it MECA, but it stood for something else. And this one has a whole bunch of wet chemistry cells in here, but this is the sample wheel. There's like 90-some sample positions on here. They dump dirt through a slit in the case, lands on this part of the wheel, they spin it around, the excess falls off, and then they can move this thing up to the focus of this microscope. This one was built with 4 microns per pixel resolution. And this is what the front of it looked like. We had red, green, and blue LEDs plus some UVs. It turns out that the PI for this instrument, which is at JPL, realized that if in this dust that we were going to put in this instrument, there was any diatoms or microscopic remnants of sea creatures, what becomes diatomaceous earth, their skeletons will fluoresce. So he wanted UV LEDs so we could check and see if there was anything in there that would fluoresce. Now, there's a bunch of chemicals that will do that too, or minerals that will do it, but that would be an interesting experiment. They didn't find anything right away, nothing for us, so. So we got to go to the Phoenix launch. Took my wife and a couple other relatives there. I don't think I even tried to shoot pictures. I did it up. But the exhaust from the rocket formed this noctilucent cloud, and it got sheared and twisted and turned by the winds until it looked like the Phoenix logo. And Peter's like, "Oh, that's a good omen, man. We're gonna land and we're gonna do good." Anyway, now this is a high-rise picture, and you can't see it in the picture because it's a 20,000 pixel wide picture. Right here, there's a little white thing. That's this. That's the Phoenix lander and its parachute on its way down. So they actually changed the orbit of the high-rise to be at the right place at the right time, and they slewed the camera over so they were looking at a steep angle to the ground. This crater is like 20 kilometers away from where we're going to land, and we're still 10 kilometers in the air. They figured out what time to run the scan to catch an image of this. So that was a pretty good trick. I was just flabbergasted when I saw that. And then later on, after we landed, they took a picture of us on the ground. These are the two solar panels, and that's the lander. There's the back shell on the parachute, and there's the heat shield. It's nice to have confirmation from orbit that, yeah, you really did make it to the ground, and things deployed. So we started getting images back. I got to be on the operations team. That was fun, I'd say, but it was quite demanding. I started on uplink, which meant we edited sequences to be sent to the lander to be executed the next Mars day. So we worked on Mars time. We worked during the Mars night, and it took us about 8 hours to edit sequences, get them merged, get them tested, do all the things we had to do. We had to do a bunch of quality control stuff, the software, and eventually they came up with the program load, the command load for the lander to go the next day. It got integrated into a bunch of engineering stuff and then beamed up to an orbiter, which would then beam it down to the lander. We didn't do much communication with the lander direct. Everything was through orbiters. Problem is, a Mars day is 24 hours and 39 minutes long. So every day you're slipping relative to Earth time. And although I slept okay, a lot of people couldn't sleep very well, but I slept okay, but I just never felt like I was 100%. It just always felt like I was dragging. I don't know what that was, but my bio clock did not like that. And I got to wonder about a Martian astronaut, if they're ever going to adapt to a 24-hour and 39-minute day. I don't know. In 3 months, I didn't. But after 3 months, we were in the extended mission, and we got to do sequences for 2 days ahead. They started planning further ahead. And so we could work on Earth time, and the sequences either run the next day or the day after that. So that was very nice.
I got longer day or shorter day. Wouldn't it be easier to adjust to a longer day? For instance, if you're going from the U.S., from Europe to the U.S., it's a little easier.
I don't know. All I know is that 24-hour and 39-minute day, or 36-minute day, I was just dragging the whole time. I just felt, and when we went to the standard Earth days, man, I just felt good. This is how we do color calibration. We have a monochrome CCD, we have a color filter wheel to calibrate everything to make sure you get an accurate color image on Mars. We have color standards on the deck. Here's one of them on the corner of the deck. This is what it looks like in a full color picture. There are magnets underneath these silicon targets that have minerals in them because they can withstand the UV and not change color. the magnets pull the dust out of the air before they get to the center of the target, so the center of the target stays.
How do magnets pull dust out of here?
Most of the dust in Mars is iron oxide. It's all magnetic.
Okay.
Yeah, it's hematite and various types of goethite and various types of iron. These are the targets in other parts of the deck. There's 3 targets around, so depending on what's illuminated by the sun, we can always shoot 1 target. After several days being on the surface, deploying the cameras, getting everything working, they decided to take the robotic arm and the robotic arm camera and look under the deck. And what they wanted to see was, well, what did we do to the surface where we landed? And the moment the science saw this guy, they said, holy cow. We blew away all the dirt, and that's the ice glued together dust, dirt, everything that's down there with very hard ice. Ice is very hard because it's very cold. We essentially excavated down to the ice table. And we're working so hard to dig out there in the workspace to get to the ice table, and here it is, been there all the time. It was nice to see. Of course, all this stuff is contaminated with byproducts of hydrazine exhaust. So they know what that is, and if they see that stuff in any of the tests, they know how to account for it. So this is the first real smoking gun of absolute detection that we had water ice there. I think that robotic arm camera image was after this. So it was like Sol 30 or something. On Sol 20, they dug, and in the corner of this trench, there was these whitish lumps. Now everything's red, it's whitish red, and it's just, it's just lighter. And it's whitish because it's glued together, dust glued together with ice. After 4 days, and them not touching anything in here, these things just disappeared. The ice sublimated away, left a little pile of dust there. So that was pretty conclusive evidence that those chunks were ice, and that the areas here that look whitish, that's water ice. They're a little overexposed because when they get this correctly exposed, this stuff ends up being kind of overexposed. Okay, now we're back to 3D. Oh, press the wrong button. So the image on the left is the dump pile. And you'd think this wouldn't be very interesting, but we took a lot of images of the dump pile. Because this is all the stuff we've gone through in digging the trenches. And there we took a lot of spectrographic images where we do all the geology filters of a chunk of this pile. They looked at the angle of repose. They looked at the stuff that kind of rolled off on the backside. I mean, they spent a lot of time looking at this stuff. This is just an area of the work area outside of where we were digging, which was down here. But this is what the ground looks like, and you see it kind of has a contour to it. So this is probably the edge of one of those hexagonal cells that we landed on. And here's a couple of stereo images of the trenches. And you can see that we dig down. The digging was pretty easy until we hit the ice layer, and then it was like digging in concrete. It was very hard. And they would just scrape and scrape and scrape and scrape, and you'd get a little bit in the scoop. But they dug in several different areas, trying different things in the digging and trying to see how the ice layer varied by position in where we were. Now, this is not a 3D image. This is the midnight sun on Mars. So we landed on Mars above the Martian Arctic Circle. So when we landed, it was summer. Sun never sets. So here's the sun coming close to the horizon, but never really setting. You can see the images here are a lot dimmer than they get out here because we're looking through a lot more dust. This is a composite image. It's, of course, all the separate images we took of the sun in their proper place. And then there's You would, with a solar filter, you can never see the surface.